welcome you all in the 22nd lecture of Electronics Measurement and Instrumentation. In this lecture, I will discuss frequency counter and frequency meter. So, this is the outline of my lecture. First, I will discuss what is the frequency counter. In previous lecture, I have discussed about the different counters, that is the asynchronous counter, synchronous counter and the decade counters and the application of the counter. So, here the application of the one of the application of the counter is in frequency counter. So, here I will discuss the frequency counter, advantage and application of frequency counters and types of frequency counters, and then I will discuss the digital frequency meter. So, you can see that frequency counter is look like this, and it counts the number of pulses that is applied to any device. So, frequency counter is used for the accurate measurement of frequency of any signal. These are used to measure the accurate frequency of signal generated from any square wave generator or any oscillator. The basic operation of the frequency counter is based on the AND gate. We can understand the function of a digital counter by using AND gate. So, we note that the AND gate has a property that when both inputs are 1, then it will only produce 1. If any one input of the input of AND gate is low, then it will produce low output. So, suppose here we are using signal whose frequency we want to count, measure. Then what is frequency? Frequency is the number of cycles that appears in 1 second. So, suppose we have generated a pulse of 1 second, and at one terminal of AND gate we have applied 1 second pulse, and the other input of AND gate, the clock pulse is applied, the pulse is applied whose frequency we want to measure. Then this AND gate will open for 1 second and it will pass the number of pulses in 1 second. So, since each pulse represent a cycle of the unknown signal, the number of counts that is produced by the AND gate is direct indication of the frequency of the unknown signal. This frequency counter or the using this AND gate or other digital equipments has very high frequency of operation. So, AND gate 1 second whatever the number of pulses are passed through that AND gate, that is counted by the counter and it will represent the number of the frequency of the signal. This is the basic circuit of frequency counter. In a frequency counter, the unknown signal is applied to the Schmitt trigger. Schmitt trigger is a circuit which converts any type of waveform into square waveform. So, Schmitt trigger maybe we can make it using operational amplifier simply with the positive feedback. So, op-amp we know that when it is used in open loop, when there is no negative feedback. So, when it is used in open loop or in positive feedback, since the gain is very high 10 to the power 5, then the Schmitt trigger will produce plus Vset minus Vset. So, it means Schmitt trigger converts any type of waveform, whether it is triangular waveform, it is sinusoidal waveform, it converts it into square waveform. Then that output of Schmitt trigger is fed to the start stop gate. So, when this Schmitt trigger output is fed to the start stop gate, then the first pulse, the leading edge of the first pulse appears at the start gate opens and the number of pulses are passed through this, and when stop pulses pass through this start stop gate, stop pulse is applied from here, then it will stop the gate, stop the gate functioning, and then there is a counter and the counter will count the number of pulses, and then there is a digital readout device that will display, that is display device that will display the number of pulses. So, in this way we can count the number of pulses. So, there are important function important blocks, that is, one is Schmitt trigger is very much important block, and that is the start stop gate, and then AND gate, counter, and the digital display unit. So, this is circuit, some expansion of the previous circuit. So, here we can see that an accurate time base or clock generator is there. The clock generator is basically it is a crystal oscillator, because crystal oscillator is very stable to generate high frequency. So, high frequency is generated by the crystal oscillator. Then this is fed to the decade divider. Decade divider is basically decade counters that we have studied in last lecture. So, these decade divider, decade counter divides, and suppose this generally the crystal oscillator produces the frequency in megahertz, 10 to the power 6. Now, we want low frequency, suppose 10 to the power 3. So, we can use 3 decade counters in cascading form. So, the first decade counter will reduce it from 10 to the power 6 to 10 to the power 5, the next 6 to 10 to the power 5 to 10 to the power 4, and so on. So, decade counters are used. Then there is a gate flip flop. So, when gate flip flop will open, it will generate, suppose we want to generate one pulse of 1 microsecond or 1 second. So, that is decided by the gate flip flop, and then it is fed to the AND gate. The incoming signal that we want, the frequency, whose frequency we want to measure. So, that incoming signal is if the signal amplitude is very low, then we need an amplifier to amplify the signal. So, that is the input conditioning and threshold. If it has high value, then we have to reduce the amplitude of the signal. Then this signal is fed to the amplifier circuit and signal conditioning, then it is fed to the gate. Again the gate will open for this time period, that is decided by this pulse, and for this time period whatever the number of pulses pass through the AND gate, that is counted by the counter, and this counter will store the number of pulses, and after when the counting finishes, then it will fed to the display unit, and display unit will display the counting, the frequency that is counted by the counter, and the display unit will store that unit till the next pulse, or till we reset the counters. So, now advantage of frequency counter. Frequency counter measures the frequency of the pulse generated from a square wave generator at a precise time interval, and it is widely used to measure frequency within the RF range. Suppose we have a very high frequency range, that is the radio frequency range, then these counters, these frequency counters are suitable for that, and they provide accurate frequency value very quickly, and ensures that all the frequencies are transmitted within the specific band. So, now application of frequency counter, we can use these frequency counter to count number of pulses, we can use in data transmission. These are also used for the measurement of the frequency very accurately, and it is also used to measure the frequency of the oscillator, that if we have designed any oscillator and we want to ensure whether the frequency generated by the oscillator is same what we have designed, then we can measure the frequency by these counters. And they also detect the frequency if there is any impulses or high frequency signal is in the transmission line, then these frequency counter can detect those number of pulses. Type of frequency counter, there are many type of frequency counter, like bench frequency counter, that type of frequency counter generally used in the laboratories, in academic institutes laboratories. So, these bench frequency counters are placed at a bench, and we can measure the frequency by this counter. The next is PXI frequency counter. So, PXI this type of frequency counters are fixed in a rack. So, rack systems are used in the industries. So, where the equipments are in the form of card, and these cards are inserted in a rack. So, PXI frequency counters are placed in a rack, and it is very, it can be a part of very sophisticated test system. Then handheld frequency counters. So, handheld frequency counters are those counters that we can use like we are using a digital multimeter. So, we can use it very easily, and it can counts very easily the frequency. So, handheld means we can place it from one place to another place, we can take it to measure any place. Then frequency counter in a digital multimeter. Most of the digital meter also has a facility of measuring frequency, although they are not very accurate measurement, but yes, we can measure we can measure the frequency by using digital multimeters. So, in digital multimeter, no coaxial RF connection is available as the test probe, and so it may have a false count triggering and other things. So, not much accurate, but we can measure the frequency. Then it is also available in the form of panel meters. Frequency counters are available in panel mount modules. So, they can be incorporated in the large items of equipment where they can be used for counting frequency or the time interval. Now, there are different type of errors in the frequency meter, that is the first is time based error. Although we are using crystal oscillator, but crystal oscillator frequency is also crystal oscillator generated frequency also depends on the temperature. So, if there is no temperature stability, then the frequency, the clock pulse generated by the crystal oscillator will have some error, or it may not be accurate. Then the effect of the main or line frequency, line variation is also there. If the variation is power input is there, then it will create a variation in the crystal oscillator. Aging error is there. If a crystal oscillator we use for a long time, then it will not produce the accurate frequency, the signal of accurate frequency. So, calibration is time to time calibration is required whether the crystal oscillator is producing the accurate frequency or not, otherwise error will happen. Similarly, the count error is there. So, we can see here in the diagram that if the counter start counting at this place, then it will count only 2 pulses, but if it is start here, it will count 3 count. If it start here counting, so slight time difference means there is if no simultaneous appearance of the input signal whose frequency we want to measure, and the this time based generator frequency, then this type of error may happens, means it can count 1 or 2 clock pulses less, or it can count the 1 or 2 clock pulse more. So, this is plus minus count error is there. Then triggering error is there, if the triggering time of the frequency counter has any error, then it will produce error in the overall system. Systematic error is there. This form of measurement error on the test equipments occur and the result of mismatch between the start stop channel. So, it may result difference in the channel rise and fall times. So, propagation delay is also there. So, these are the type of error that can create in a frequency counter system. Now, digital frequency meter. This is the block diagram of digital frequency meter. So, here we can see that the clock pulse is generated by the clock oscillator, and it generally generate 1 megahertz clock pulse. So, crystal oscillator is very stable oscillator, that is why crystal is used for the oscillation purpose. When pressure is applied, it produces a frequency, and it will withstand with the temperature and other changes more than the other type of oscillators. So, crystal oscillators are preferred. Here we can see the crystal oscillator generates and it generates sinusoidal waveform. So, that sinusoidal waveform we have to convert it into a square waveform. So, this oscillator frequency, if amplification is needed, so amplified this frequency is amplified and it is fed to the Schmitt trigger. The purpose of a Schmitt trigger is to convert it into square waveform. Then this frequency is high, we want to convert because when we want to measure the frequency low frequency signals, then we have to divide it by 10. So, there are many ranges time based selector switches there, and there are range of frequency that we can measure. So, this 1 megahertz frequency is divided by 10 10 10 means here the 1 megahertz crystal frequency means the time period is 1 microsecond. So, when we place our time based selector at this position, then it will produce a pulse of 1 microsecond, and it will count the number of pulses that is passed in 1 microsecond. Suppose if number of pulses are less, then this switch is placed at this position, and similarly at this position. So, these are the decade counters. These are the divide by 10 counters. So, decade counters we can use here for the dividing this generated frequency. So, these are the decade counters, and then we can select the time period as per the requirement of the input signal. Then input signal is applied to the Schmitt trigger circuit. Again, input signal is of any form, and when we want to count the number of pulses, we have to convert it into Schmitt trigger. So, if amplification is required, so the signal is amplified. If the amplitude is very high, then it may be attenuated by the attenuators, and then it is fed to the Schmitt trigger circuit. Schmitt trigger circuit converts it into pulse form. Here the pulse is applied through the Schmitt trigger again, because if there is any distortion occurs, then it will be now complete square wave is there, and after that there is a gate flip flop. So, gate flip flop will, when the Schmitt trigger will switch on this gate flip flop, then it will produce a pulse. It will fed a pulse of the duration that is selected from this time based selector switch, and then the gate AND gate will open for that time period of time, and it will pass the number of pulses that is passed in this time period, and then when the counter stops counting, then it is fed to the counter, and counter start counting, and when the counter stops counting, at that time it will send a pulse to the readout device, and readout device will display the number of frequency that is counted by the counter. Now, this is the in previously this was the gate circuit. So, this circuit is explained in next. This is the internal block diagram of the gate control flip flop. This gate control flip flop basically switch on and switch off the AND gate, which is the main gate that is placed here, so that it can feed the signal to the control the counter. So, here initially the flip flop 1, this flip flop 1 is at logic 1 state. Initially it is at logic 1 state, and the resulting voltage from output Y is applied to the this Y. When it is at set state, the Y is high and Y bar is low. So, Y is applied to the stop gate, and this at point A of the stop gate, and it enables this gate. So, initially it is at set position, when it is at set position, Y is high and Y bar is low, and when Y is high, the A input of this AND gate, stop gate is high, and when this input is high, it means this stop gate will produce 1. Okay. So, it enables this because here the time pulse is there. So, B input is already high, the A is high. So, it means both the inputs are high, and the stop gate will produce high output. So, when it will produce high output, it will set the flip flop FF2. So, the stop gate enables the gate, the logic 0 state of the Y bar of the flip flop 1, when the logic 0 state will appear, then when this is at logic 0, then it will produce Y bar high, and when it will produce Y bar high, the when it will produce Y bar high, then it will start the gate. So, when Y bar is high, flip flop 1 is applied to the input A of the start gate, and start gate start functioning, and it will start gate's input is high. So, it means it will reset the flip flop. when it will reset the flip flop 2, it means the output of this, when it is reset, the y bar is high and it will enable the main gate. So, as the stop gate is enabled, the positive pulse from the time base generator passes through the stop gate and set the input of the flip flop 2. Thereby setting flip flop 2 at one state means keeping it off. So, we can understand the working this, that the pulse from the time base generator is fed to both the AND gate, but initially it is in off state. So, when it is in set state, it means it is producing y high and the stop gate is on, stop gates both input is high. So, stop gate will set the flip flop 2 and flip flop 2 will produce a y, set it, and y is high, y bar is low, and then the main gate is not functioning. So, when this read pulse is applied to reset flip flop, so what will happen because of this read pulse, it means ki now start the indication of this read pulse is now start the counting of the input pulses. So, when input pulse appears, the read pulse will go high, and when it will go high, it will reset this flip flop FF1. When it will reset this flip flop means the y bar is high, and when y bar is high means the one input of this upper AND gate, that is the start gate, is high, and when A is high, it means both input of start gate is high. So, start gate will pass this pulses from the time based generator circuit, and then it will reset the flip flop 2. When it will reset the flip flop 2, it means the flip flop 2 output y bar is high, and when y bar is high, it will enable the main gate. So, when main gate is enabled and the input is applied, input of unknown frequency is applied, if the input is high, if the input voltage is high, then we need an attenuator to attenuate that input voltage. But if the input frequency, if input voltage is not sufficient to switch on the trigger circuit, then we need to amplify that unknown frequency signal. So, unknown frequency signal is either attenuated or amplified and then fed to the Schmitt trigger. A Schmitt trigger is again a circuit that converts any type of waveform into into a square wave. So, that the input signal which is of any type, any form, it is converted into a square waveform, and that square waveform is applied to the main gate. So, main gate one terminal, that is the terminal B, is having a range that previously we have discussed, that the range is selected from here, and these range whatever range we have selected, by this range for this time period, suppose we have selected this point. So, it means it is 100 microsecond pulse is there. So, here it is generating 100 microsecond pulse, and this gate is open for the 100 microsecond and this input signal is passed through the 100 microsecond. So, the number of input pulses or input square wave is passed through the AND gate, and then it is counted by the counter. So, counter will again it is converted into frequency, means it is the counting is in 100 microsecond, but it is converted into seconds, and then it defines the frequency. So, counter's main function is to count it, and then there is and the display device is calibrated in terms of frequency, means the displaying device will display the frequency, that is the number of pulses that will pass in 1 second. So, now application of digital frequency count meter. We know that the digital frequency meters have very much application, because if we have designed any oscillator circuit, then we need to specify whether our circuit is working properly or not, or whatever we designed the circuit for that particular frequency, that frequency is the circuit is generating that frequency or not. So, we can use the digital frequency meter for the measurement of the frequency generated by any designed oscillator. We can also measure the frequency of a transmitted carrier So, when we want to measure the frequency of the transmitter carrier, then we should not modulate that signal, we can measure the frequency it. After modulation it is not possible to measure the frequency. So, we can measure the carrier frequency, we can measure the modulating signal frequency also, we can measure the frequency of the line signal when the electricity is supplied. So, whether the electricity supplied electricity has a frequency of 50 hertz or not. So, we can check that value using digital frequency meter, or we can use using any frequency meter we can measure it. Then so we can measure any type of steady repetitive signal amplitude by signal frequency by using digital frequency meter. When we want to measure a high frequency signal, that is the radio frequency signal. So, there are few prerequisites, that is the condition that is to be fulfilled by the meter, that is the frequency must be steady, means there is no change in frequency, no variation is there. So, frequency is in the form of steady, means same frequency is generated, then only the frequency meter can measure the frequency. Then the signal should not be modulated, because if signal is modulated the frequency is changed. So, when we want to measure the frequency of carrier or the amplitude modulated signal, or the signal which we want to frequency modulation done, then we have to measure the frequency before the modulation process. Then that signal should have sufficient amplitude, means it should operate the digital frequency meter. Suppose if amplitude is very low, then we can't measure the frequency, and if amplitude is very high, then again we have a problem for measuring the frequency. So, it should be in the range of minimum is half volt, then we can measure it, and signal should be not very large, so that it can not overload, it should not overload the input signal. So, in this lecture I have discussed the different type of frequency counters, frequency meter, what are the basic function of different blocks that is available in the digital frequency counters. So, thank you all.